Hello, everybody. I will wait about 30 more seconds and then we'll get started. Okay. So I've got a pretty quick lesson for you guys today. If you forgot the midterm for this past triad is now open. So for that reason, I'm gonna give, I'm gonna have simple lessons, and we're just gonna do really quick quizzes for these lessons. So I'm trying to give you a little bit more time since I know the midterm is going to suck up a couple of hours for you maybe this week. Okay, so let's go ahead and get started. So what we're going to be talking about today is something called the intensity of waves. Okay, so the intensity of a wave is a measure of the energy carried by the wave. Okay. So what I want to imagine is the following. I want to imagine a source of a wave, and that source is, and then there's like a wall over here. So I'm trying to draw this like a three-dimensional wall, if you will. Okay, so here's a wall, and the wall has area A. All right. And so the so then the source is emitting waves, and those waves are hitting the wall. Okay. Now, because the source is emitting waves continually, okay, there's a certain rate at which the source is emitting energy, and so there's a thing called intensity, all right, which is the energy absorbed by the wall divided by time, and also divided by the area of the wall. Okay, so length times width if it was a rectangular wall. Okay, so energy absorbed by the wall divided by time divided by the area of the wall. That's the definition of intensity. Okay, intensity is denoted by I. So if I were to write that more compactly, it would be I equals energy per time per area. Okay? We're going to learn more about this concept later on, but there's something called power, which is denoted by P, and power is energy per time. Okay? So actually we could write the formula for intensity a little bit more simply as power per area. So intensity is the power per area. And power is energy per time. It is the rate of output of energy. So if you have a large power output, you are outputting energy very quickly in a short amount of time. So let's figure out the units of these quantities. So the units of power, well, power is an energy divided by a time. Energy is measured in joules. Time is measured in seconds. So power is measured in joules per second. Okay. 1 joule per second is also known as the watt, W. Okay, so power is measured in watts. It's also measured in horsepower. Okay, I believe that 1 horsepower is like 746 watts, I want to say. But the unit that we'll be using is watts. So if you buy a light bulb, okay, and you look at the box that the light bulb is in, it will tell you the wattage of the light bulb. So if it's an incandescent bulb, it'll say, maybe 60 watts or something. So 60 watts means that that light bulb, when you plug it into the socket, is consuming 60 joules of energy per second to produce that light. Okay? If you buy an LED bulb, LED bulbs are more efficient, so it might only be 10 watts for an LED bulb. Excuse me. So anyways, once we know what power is, we can then talk about the units of intensity. The units of intensity are going to be units of power divided by units of area, which is watts per square meter. So that is the unit of intensity. Okay. And there are many other units of intensity. For example, decibel is a unit of intensity. You might have heard of decibels before. That's a logarithmic unit of intensity. So let's just do a quick example with how to calculate intensity. All right. So let's suppose you have consider a 4 meter by 3 meter wall that is absorbing let's say 90 joules let's say 900 joules of energy, and I'll say sound wave energy, because usually intensity is referring to the energy carried by waves. It's absorbing 900 joules of sound wave energy each minute. What is the intensity? Okay, so first of all, it's a wall that's 3 meters by 4 meters. So that means that the area of the wall is 12 square meters. And then we have to get what is the power absorbed by the wall. Okay, so the power absorbed is the energy absorbed, which is 900 joules, divided by the time that it took to absorb that amount of energy, which was 1 minute. We want to put that in, in standard units, which would be seconds. So we have 60 seconds. So that is 15 joules per second, also known as 15 watts, is the power absorbed. Okay, so then we can put these two together to calculate the intensity. Intensity is power absorbed per area. So that would be 15 watts in an area of 12 square meters, which is 1.25 watts per square meter. Okay, so that would be the intensity that the wall is experiencing. All right. So the next question I want to discuss is, how does intensity vary with distance from the source? Okay, so imagine, you're out in a field and you're yelling. If someone is really close to you, they're going to hear that yell, and it's going to be loud. Okay, so that means intensity is related to volume of a sound wave. Okay, so intensity. So if the observer of you, or the listener, I should say, of you yelling is close, they will experience a high intensity of sound waves. Okay? If the observer is far away, they will not experience a high intensity of sound waves. In fact, they might not be able to hear you at all because you're so far away. The intensity of the sound wave is so low that they can't detect that there's a sound at all. Okay? So intensity decreases as you get further away. All right. Same thing is true with light waves. So for example, the stars in the night sky, okay? If you look at the stars in the night sky, many, many, many of those stars are brighter than the sun. They're emitting more energy than the sun is. But intensity is kind of relative to your location, right? It's how much energy are you receiving from your location with your size, okay, with your dimensions. And so we are so far away from stars other than our sun that the intensity of light by the time it reaches us is low enough that we can just look directly at the stars in the night sky, okay? If we talked about the sun and the star in our solar system, the sun, it's close enough that the intensity of sunlight is enough to damage our eyes, okay, if we look directly at it. It's because there's less distance, so we get a higher intensity. Even though some of those other stars are brighter than the sun, many of them are, intensity is relative to your distance to the source. And so the sun is the most intense star that we experience, okay? So there's a nice formula. It says that the intensity is P over 4 pi r squared. Make that capital R, I think that's easier to read. So P is the power output of the source. Okay. R is the distance from the source. Okay, so we can see that R is in the denominator, so that as R goes up, you're increasing the size of the denominator, so the intensity will go down. Important point about this formula, this assumes the source is, and I'm going to use a fancy science word here, isotropic. Okay. So isotropic means that it is emitting waves equally in all directions. Okay. So let me give you an example of a non-isotropic source of waves. Okay. Your voice. Your voice is not isotropic because your voice is sending out more waves in the forward direction than it is behind. Okay? So that's non-isotropic. Another example of a non-isotropic source is a laser. Okay? A laser is sending light waves, almost all of them in one direction, and then almost none in every other direction. Okay? A street light is non-isotropic because it's emitting most of the light waves down towards the street and not any at all up towards the sky. So those are our non-isotropic sources. If we look at something like the sun is a star. It's emitting light the same way in every direction. So the sun is an isotropic source. Okay. Another example would be like a tsunami siren. Okay. If you've ever gone to the beach and seen like those tsunami sirens, it's like they have speakers pointing in every direction, so that it doesn't matter where you are, you're going to hear when the alarm goes off. Those are isotropic sources. Okay. So, I need to look at something for this next question. Okay, so let's do a problem that involves the sun. All right. So let's say the sun has a power output of 3.8 times 10 to the 26th watts. It's a huge power output, okay? So 3.8 times 10 to the 26th joules of luminous energy are leaving the sun per second. It's a huge, huge amount. We are 1.5 times 10 to the 11th meters away from the sun. Okay, what is the intensity of sunlight at the Earth? Okay, so we're just going to plug it directly into this formula. Intensity is power, 3.8 times 10 to the 26th, divided by 4 pi 1.5 times 10 to the 11th squared. And we get about 1350 watts per square meter. Okay. Now, something that I find interesting about this, at least, is this is the intensity in space above the Earth. But we don't actually receive down here at the surface of the Earth, we don't receive that much intensity because the atmosphere absorbs some of that energy. Okay? So by the time that sunlight actually reaches us, it's reduced the intensity to about 1,000 watts per meter squared. Okay, so this is at the surface. Okay, due to the atmospheric absorption. So, you know, you would sunburn more easily in outer space because the atmosphere isn't blocking the luminous intensity. And then another interesting thing is solar panels are about 10% efficient. Okay. So what that means is that solar panels are receiving 1,000 watts per square meter of sunlight. Okay. But they're only able to convert 10% of that into usable electricity. So 10% of 1,000 is 100 watts per square meter. So if you have a 1 meter by 1 meter solar panel, it's going to be able to produce about 100 watts. Okay? So 1 meter by 1 meter solar panel will output about 100 watts to your house during sunlight. Okay? So that's kind of interesting. So that's a good rule of thumb. If you want to know how much power is if you have solar panels on top of your house and you measure how many square meters your solar panel array is, you could estimate how much power it's giving you. Okay, from that. And of course, this depends on the sun being directly overhead. It depends on the it also depends on the weather conditions. You know, there's no clouds. It depends on there being nothing covering the solar panel, etc. Okay, so we're going to answer one more question, all right, which is the following. How does the intensity vary with the amplitude of the waves. And I think that is fairly obvious. The bigger the wave, the more intensity. Okay. So let's show how this works. So there's a nice formula. It says that the final intensity is the original intensity times final amplitude divided by initial amplitude squared. Okay. So that is a nice formula. So in particular, we could do a little example. What happens to the intensity if you double the size of the wave? Okay, so if you double the size of the wave, then that means that the final amplitude is going to be twice the initial amplitude. Dividing both sides by initial amplitude is going to tell us that A final over A initial is 2. And then if I square both sides of that, I get A final squared over A initial squared is 4. All right. So plugging that back into this equation, the final intensity is going to be 4 times the initial intensity. So if you double the size of the wave, you get actually 4 times the intensity. And in fact, if you were to triple the size of the wave, you would get 9 times the intensity. If you were to quadruple the size of the wave, you would get 16 times the intensity. See, it depends on the square of the amplitude. So whatever change you make, that change gets squared. It gets sort of magnified, if you will. So amplitude, the main things that impact intensity are the amplitude of the waves themselves and the distance from the source. Okay? So that is my lesson for today, and